In this section on differentials, our objectives are to understand the concept of a tangent line approximation, compare the value of the differential with the actual change in y, find the differential of a function, and estimate a propagated error using a differential. Let's take a look at the definition of differentials. Let y equal f of x represent a function that is differentiable in an open interval containing x. The differential of x, denoted by dx, is any non-zero real number. The differential of y, denoted by dy, is dy equals f prime of x dx. Differentials relate to the tangent line. Take a look at this picture where this parabola is the function, we'll call it f of x, and this is the tangent line at this point of tangency here. So the picture that you have is a zoomed in shot of that function, that's f of x, and the tangent line. Notice how when we zoom in on that area where that point of tangency is, that the tangent line and the function look almost like the exact same thing. That's the idea behind the tangent line approximation. So this change in x here is the difference between that point of tangency right there and the point that we're trying to approximate on the curve, which is noted up here. So this change in x from this x value to this x value, which can be called delta x for change in x, is also the differential dx. This change in y, if we look from this y value to this y value of the point to approximate, is the change in y, but the differential is the change in y on the tangent line. So notice that we're referring to the tangent line when we talk about the differential. The dx, the change in x on the tangent line, and the dy, the change in y on the tangent line. So bringing your notice to here, how dy, which is approximately delta y, is the change in y of the tangent line, which is approximately the change in y of the original function. Dx, which equals delta x, is the change in x of the tangent line, which equals the change in x of the function. So let's remind ourselves how we write the tangent line of a function f at the point c, f of c. Y minus f of c equals f prime of c times the quantity x minus c. You may feel more familiar with y minus y sub 1 equals m times the quantity x minus x sub 1. Well, that's the same. This is our x sub 1, and this is our y sub 1 in this point right here. How do we find the f prime of c, or the slope? By taking the derivative. So our m, or f prime of c, is the dy dx, which equals the derivative of the function, or f prime of x. So notice if we take dy dx equals f prime of x and solve for dy, then dy equals f prime of x times dx. Notice that's what the differential of y is shown as here. Dy equals f prime of x dx. A tangent line can be viewed as a linear approximation or a tangent line approximation to a function. Delta y is approximately dy, which equals f prime of x dx. Or the change in y of the function is approximately equal to f prime of x dx when dx is small. So notice again, dy approximately equals delta y. The change in y of the tangent line, that's the dy, is approximately the change in y of the original function. That's delta y. And remember, another way that we found delta y before is f of x plus delta x minus f of x. Remember the difference quotient with delta y over delta x? And dx equals delta x, which means the change in x of the tangent line, that's our dx, equals the change in x of the function, delta x. Differentials can be used to approximate function values. F of x plus delta x equals f of x plus delta y, which is approximately equal to f of x plus dy, because delta y is approximately equal to dy, which equals f of x plus f prime of x dx, because dy equals f prime of x dx. So what will be helpful for us to remember is that f of x plus delta x equals f of x plus f prime of x dx. Let's take a look at some examples that use differentials. Number 1, let y equal 1 minus 2x squared. Find dy when x equals 0 and dx equals negative 0.1. Compare this value with delta y for x equals 0 and delta x equals negative 0.1. So first of all, we remind ourselves that dy equals f prime of x dx. So dy equals the derivative of y, which is negative 4x, times dx. So dy equals, with x equals 0 and dx equals negative 0.1 plugged in, negative 4 times 0 times negative 0.1, and that makes 0. dy equals 0. The differential for y is 0. Now let's find delta y. So we recall that delta y equals f of x plus delta x minus f of x. The x value is 0. The delta x value is negative 0.1. 0 minus 0.1 makes negative 0.1. Plugging these values into our function, this is our f of x, gives 1 minus 2 times 0.1 squared minus 1 minus 2 times 0 squared. This gives us negative 1/50th for delta y, and comparing them, notice how negative 1/50th is a very small number, very close to 0. Are they the same thing? They are not, but they are very close to each other. Remember, dy is approximately equal to delta y. Number 2, find the differential dy of the function y equals square root of 9 minus x squared. So again, we recall that dy is f prime of x dx. So basically, they're just saying take the derivative of this function. So let's do that. Let's rewrite this in a more derivative-friendly way with the exponent, and then we can use our power rule and chain rule. 1/2 multiplied to the front, 9 minus x squared. Subtracting 1 from the exponent gives negative 1/2, and then the derivative of the inside, negative 2x. dx at the end, and then we can clean that up a bit. 1/2 of 2 is 1, so we end up with negative x over negative exponent, sends it to the denominator, and it is the square root 9 minus x squared dx. And there's our differential dy. So notice this is very similar as saying dy dx equals, but the dy stays here and the dx goes over there. Let's look at how we can use differentials to approximate a function value. Number 3, use differentials to estimate the square root of 15.6. So obviously with a calculator we can plug it in, but we don't need to do that with differentials. If this is the square root of 15.6, we want to use the square root function as our f of x. So first we define what f of x is, the square root of x. Well, what is a number close to 15.6 that is a perfect square? 16. So x will be 16. How far off of 16 is 15.6? 0.4 subtracted from 16. So our change in x, or our differential of x, dx, is negative 0.4. We're looking for the square root of 15.6, and that's x with the change of x added onto it. So we're looking for f of x plus delta x. Remember that that's approximately equal to f of x plus f prime of x dx. So what do these things mean? Well, this part is the square root of the 16 plus the negative 0.4. That's how we get our 15.6. The f of x is our square root of x function. The f prime of x is the derivative of our square root of x function, which is 1 over 2 square roots of x dx. So this part is what we're looking for, the square root of 15.6. Square root of x with x plugged in is square root of 16 plus 1 over 2 square roots of 16 times dx, which is our differential negative 0.4. Computing this side, the square root of 16 is 4 plus 1 over 2 times 4, or we'll leave it as 2 times 4 because negative 0.4 can also be written as negative 4/10, and I like that because we can simplify there, and then I can do 4 minus 1/20, which is the same as 80/20 minus 1/20, or 79/20. Now if we type that into a calculator, we get 3.95. How close is that to the actual value? Well, let's just take a look. The actual value, if I used a calculator for the square root of 15.6, is approximately 3.94968. It keeps going because it's irrational. And comparing these, notice this is almost 3.95, but it's less. Notice in this function right here, this is the square root function, f of x equals the square root of x, and this is the tangent line here. Notice that the tangent line is above the square root function. So our tangent line approximation will be more than the actual value. Let's make a note of that from the picture to notice that the tangent line is above f of x. Therefore, the approximation, or the estimate, is greater than all of the actual values we might calculate. Error propagation. Physicists and engineers tend to make liberal use of the approximation of delta y by dy. And one way this occurs in practice is in the estimation of errors propagated by physical measuring devices. Because nothing's perfect, so there's going to be an error when we measure. Propagated error. If a measured value x is used to compute another value f of x, the difference of f of x plus delta x and f of x is the propagated error. That's what this shows here, the difference of f of x plus delta x and f of x. So this is the exact value because x is the measured value, and there's some error possible with our measuring devices. So this delta x is the measurement error. So take our measured value, add it to the measurement error, it gives that exact value. So the difference between what we get with the exact value and what we get with the measured value gives us our propagated error. The relative error is useful for knowing in order to determine if our propagated error is large or small. That's the ratio of the error to the actual measurement, or dy to y. And the percent error is helpful in just converting it to a percent. So taking our relative error, dy over y, and multiplying by 100 for the percent. Let's try an example. The radius of a ball bearing is measured to be 0.8 inch, 0.8 of an inch. If the measurement is correct to within 0.02 inches, use differentials to estimate the possible propagated error in computing the volume of the ball bearing. Then find the relative error and the percent error. So it was measured to be 0.8 of an inch, and we know this measurement to be correct with a possible error of plus or minus 0.02 inches, meaning we could have measured over by 0.02 of an inch or under by 0.02 of an inch. So the radius was measured to be 0.8 inches, and the delta R, or dr, is positive or negative 0.02 inches. Again, that's also dr, just like that's the dx and the delta x are the same. Positive or negative because it could be measured over or under by that much error. How do we find the error in computing the volume? Well, that means we need dV. Here's the volume of a sphere equation. We'll take the derivative of that. dV equals 4/3 pi is our constant multiple. The derivative of the r cubed is 3r squared times dr. Now we can plug in the values that we have to help us find dV. 4/3 pi times 3. The r is 0.8 squared, and the dr is plus or minus 0.02. So we can work this out to be plus or minus 32 over 625 pi, or approximately plus or minus 0.161 cubic inches. So the error in computing the volume was approximately 0.161 cubic inches. Is that a large or small error? Well, that's what relative error will show us. Next, let's find that relative error. The relative error is the ratio of the error, dV, to the actual measurement of the volume. Remember earlier when we found dV, this expression, let's use that expression here, 4/3 pi times 3r squared dr divided by V, our volume formula, 4/3 pi r cubed. And then we can simplify 4/3 divided by 4/3, pi divided by pi, r squared comes out of r squared, and we're left with 3 dr over r for our relative error. And then plugging in the values, 3 times plus or minus 0.02 divided by r, 0.8, which equals plus or minus 0.075. Converting that to a percent error means multiplying by 100. 0.075 times 100, and that gives us 7.5%. So is the error in that measurement big or small? Well, it is relative. It depends on what's allowed. and what we're looking for, and how much error is okay to have in this measurement. Depends on the situation. So I hope you had fun with differentials, and I'll see you in class.